Hi, am I audible?
Yes, sir.
Okay, fine. Now you can see the screen as well, right?
Yes, sir.
Okay, fine. Okay, so this is second lecture on combinatorics. So, right. So first of all, let's start with multi-set. So multi-set is just a generalization of set. For an example, what is a set? So if I write, say, A, B, C, so let this be a set. So that's mean A, B, C, they are different. Right? So this is the meaning of set. So if suppose if we write say 2, 2, 3, generally we do not consider this is as a set, right? Because we as a set we write this is as only 2 and 3, right? Because when we write set, that's mean repetition does not allowed. So that was the concept of set. But what we will do here, we will just generalize that concept. So that's mean what is a multi-set? So we will take element with repetition. So multi-set is, so we can just say that here it is like a set except that elements may add more than once. Okay, I got disconnected. Okay, fine. So for an example, if I write say AA, BBB, and C, so this is a multi-set. Okay, that's when we allow the repetition of elements. And in short, sometimes it may happen that 20 times A or maybe infinite times A, right? But we generally write this is in short in this way. So 2 dot A, 3 dot B, and or you can say 1 dot C. So generally we write in this way. So this is just a notation. So this means in my multi-set, A has 2 times, B has 3 times, and C has only once. Okay. Even in the multi-set, we allowed infinity as well. So for an example, you may have multi-set like this: infinity dot A, infinity dot B, infinity dot C. So this is also multi-set. So what does it mean? So that's mean A is repeated up to infinite. That's mean it is A, and it goes up to infinite. Then B, this goes up to infinite. C, it goes up to infinite. So this is just the meaning of this set. So in short, we write this. So this is obviously an infinite set. Okay. Now if we take say 5 into A, say 6 into B, 3 into C. Now this is a, you can say that sub multiset of that the previous set this. Okay. So you can say this is a finite multi-set and this is an infinite multi-set. Okay, so the concept is very trivial, right? And we also say what is the size of a set. So it has size, it is 5 plus 6 plus 3. Okay, so it is 14. So this is the size of a set. Size of a finite set means the number of elements with the repetition. Okay, I hope this is clear. This is very simple one. Now why we are doing this? So okay, so we will see one problem, then you will understand that why we are doing this. Actually, suppose if I ask you, oops, sorry. So if I ask you to find, so this is my problem. How many solutions does this equation, so x1 plus x2 plus x3 plus x4 equal to 20, this equation have in non-negative integers? In non-negative integers. Okay, so that's mean x1, x2, x3, x4, they are greater equal to 0 and they are integers. Okay, so how many solutions this equation have in terms of integers, that non-negative integers? Now to solve this kind of problem, you need, so if you use the concept of multi-set, then you can easily tackle this kind of problem. Okay, so that is the reason we are studying now that multi-set. Okay, so do you know how many solutions are there? Do you know this? Have you
20.
seen that?
23.
Sorry?
Sir, 23C3.
23C3.
Right. So how did you calculate that?
Sir, that
We
is
say
equal
that
to
we
36.
insert 3 false coins in 20 coins.
Right. Right. So that is the same concept in the multi-set as well. Okay. So actually here in this course, we are studying this kind of solutions of this kind of equations. And then we will put some restriction as well. Some restriction in the lower bound, some restriction in the upper bound. If you have some restriction in the lower bound, then it is easy to tackle by this multi-set concept. If you have upper bound, then sometimes it is a little bit tricky to solve by only that multi-set. In that case, you can use the generating function. Okay, so we will come to this up one by one. The first, let's talk about that multi-set, because this is one application. There will be other application as well for the multi-set. So first we calculate the similar one. So same one, we generalize this problem, which you just say about, say problem. We just generalize this problem into this. So given a multi-set, say infinity x1, infinity x2. That's when x1, x2 can goes up to infinite xn. This. So this is a given multi-set, and the question is how many finite multi-set, or you can say finite sub-multi-set. Sub-multi-sets does it have of size k? Okay, that is the similar concept. Now can you tell me the solution of this one? The same way you can give the solution because it is just a generalization of this. Yes, any quick answer of this? Okay, anyway, so that is a
K
trivial.
plus n minus 1 ck.
Right, right, fine. So how we will calculate this one? So first of all, see, the proof is very simple actually. So first of all, what we will do? We have n number of unknown, right? So that unknown can be n, right? And what we need? We need the set of size k. So what we will do? We will first take, can say solution. We first take k plus n minus 1 number of blank spaces. Okay, we will just take k plus n minus 1 number of blank spaces. We just place it here. In this way. Okay, so we have, this is total k plus n minus 1, this total number, this. Okay, now just randomly put n minus 1 number of, say, star or maybe check symbol only this. Suppose you put this is 1, say this is 2, and similarly you put somewhere, say this is n minus 1 position. Just randomly put n minus 1 number of, say, star or say check symbol. Okay, then up to the first one, so this is the first, so this is the second, and this is the n minus 1. Okay, so up to the first one, up to the first check, we will write everyone only x1. And up to the, from first to second, there are some blank spaces, there are maybe no. In that case, we will not write anything. If there is some blank spaces, we will write x2. And then remaining, if we have x3, we don't know what is that. And before that check, we will write xn minus 1. And after this n minus 1, we will write only xn. This. Okay, so we are getting a multi-set. So we are getting a multi-set type of 2 into x1, 1 into x2. We don't know this one, and then 1 into xn. So we are getting a multi-set. Now that multi-set and this one, so this multi-set and this one, that is that blank and putting in minus 1, they have 1-1 correspondence. For an example, you can see this one, right? It has a 1-1 correspondence. So if you have this n minus k plus n minus 1 blank spaces, and if you put n minus 1 check, and if you have a multi-set, you can come from this to this and also this to this. So we can see another example. For an example, take, say, we will take a simple one, say k equal to 5. That is, we are interested to find a set of size 5. Say n is 3. Okay, so we have only, say, a, b, c. Only a, b, c. Or x1, x2, x3. Better to write that. x1, x2, x3. Okay. So how many spaces we will take first? Blank spaces. So k plus n minus 1. So that is 7 spaces we will take. So 1, 2, 3, 4, 5, 6, 7. Okay, this. And what is n minus 1? N minus 1 is 2. So we will just put 2 check. Say this is 1. Randomly, you can put, say, 2. This 2. So then you will write x1, x1, x2, x2, and this is x3. So your multi-set is 2 into x1, 2 into x2, 1 into x3. See, you have a multi-set of size 5, right? And you can see that 2 into x1, 2 into x2, 1 into x3. This set is same as this one. Same as this one. Right? So this is just a different kind of notation of this set. And if you have this, you can find this, or if you have this one first, then you can easily to see this one. So these are if and only. Right. So therefore, if I ask you to find number of sub multisets of size k, then you just take n plus k minus 1 number of blank spaces and just put randomly n minus 1 number of check. Okay, and the whole and what are the possibilities of number of putting this check? That is that number of possibility, or you can say number of ways, number of ways. So you have in k plus n minus 1 number of spaces, and you are putting this number of check. Okay, so that one is k plus n minus 1 c n minus 1. And someone give the answer, it is k plus n minus 1 c k. That is also right because they are same. Right, so this is the simple one. Now if we use this, then now it is easy to find the number of solutions of this equation. Okay, now what is what will be the answer here? Here your k equal to 20, n equal to 4. So number of solutions in terms of non-negative integers will be k plus n minus 1 c n minus 1. So that will be 23c3. Okay, so there is many number of solutions it will have in terms of non-negative integers. Okay, so this portion is very simple. Now if we modify a little bit, suppose we give some lower bound here. For an example, I think up to this part is clear, right, to everyone? So if you have any problem, you should ask. And also I will send you the class notes, not this one, this is the rough work. I will send you one slides which I have prepared. And also I have already sent you one one notes, not the class notes, one books you can say. Okay, so that book together with the Roshan book I will follow for this combinatorics part. So there will be, this portion is very small. So you have only around that 5 lectures is needed only. Okay, so there is pigeonhole principle and this portion. So today we will complete that. And then the next class we will see some exclusion, inclusion 1. And then we will see the generating function and recursive relation. Okay, so here is the problem 3. So find the number of solutions to the equation. Same equation we will take x1 plus x2 plus x3 plus x4 equal to 20 with, first of all, x3, x4 all are integers, and given that x1 is bigger or equal to 0, now x2 is bigger or equal to 1, x3 is bigger or equal to 2, x4 is bigger or equal to -1. Now can you tell me, so how will you proceed for this problem?
Sir, we can write x2 as 1 plus a2, x3 as 2 plus a3.
Exactly.
then the problem is similar to the previous one.
Right. Thank you. So what we will do, since we in the previous one we have seen that all are only just non-negative, right? So what we will do here, since x1 is bigger equal to 1, we can write it is as say, x2 minus 1 bigger equal to 0. Then x3 minus 2 bigger equal to 0. And x4 plus 1 bigger equal to 0. Now we just take y1 equal to x1, y1 equal to x2 minus 1, and y3 equal to x3 minus 2, and y4 equal to x4 plus 1. So that's mean we need to just find the values of y1, and here yi, and here y1, this is y2, y3, y4 all are just greater or equal to 0. Now just if we just put the values, then it will be x1, it will be y1 plus y2 plus 1, that will be y3 plus 2, and that will be y4 minus 1, that is equal to 20. And then you have just y1 plus y2 plus y3 plus y4 equal to 18, and where y1, y2, y3, y4 all are bigger or equal to 0, and they are integers. Okay. And similarly, now number of the solutions will be, now here your n equal to 4, k equal to 18, and then the number of solutions will be 4 plus 18 minus 1. This is 4 minus 1, so it is 21c3. So we are done. Okay. So similarly, if you have any kind of this kind of lower bounds, then you can solve this problem by that concept of multiset. So that is a trivial problem.
Sir, when you are taking n is equal to 4 and k is equal to 18, so which complete multiset you are considering, like that infinity into x1, where what is x1 in that, like in that?
No. We have this new problem, right? Now we have the multiset is infinite one y1. This is this multiset.
And why is the size of subset 18? I'm not able to understand it.
No, we are just taking na. Oh, sorry. This is y1. I did not get your question. Can you
Sir,
repeat?
like in theorem, we proved that number of sub multisets of size k is equal to n plus k minus 1 ck. But like how we are implementing that theorem here, like what is our multiset and what is our number of subsets of like that?
Oh, okay. So sorry. Okay. Good. So what does it mean? So that's mean, see here you have so you have a non-negative integers, right? And you are taking that equal to 18. Now suppose one solution is say y1 equal to 18. This is one solution. Say y2 equal to say 0 or maybe 1, or okay. Say y1 equal to say 15, y2 equal to 1, y3 equal to 1, y4 equal to 1. So this one, right?
Yes, sir. Yes, sir.
Okay. So for this one, say you are taking that subset, say 15 into, for an example, y1 plus 1 into y2 plus 1, sorry, not plus, comma.
We
This
are
is just a symbol notation for
into
a
y1. Like y1 is 15, but
right.
that's
So
why I'm
better to write a different symbol, right? This is the corresponding to y1. You can take a different symbol, say this one, or might be, yeah. You can take what is, so dash. So this one just.
okay. I understand.
So this is just a similar kind of thing. So that is the reason I kept same notation, but you just write a different notation y1 dash. So when your y1, the value of y1 is say 3, if your y1 is suppose k for some not k, suppose if p, then we are taking p times y1 dash.
Okay.
So it is not the exactly same. So it is actually is similar to find a multi-set, and so there is a one-on correspondence of this multi-set and this one equation. Okay.
Yes, sir.
Yeah. Thank you for asking, because maybe it is better to specify this one. Otherwise, it gives a confusion, because I am saying that your values of y1 is 15 for an example here, and I am taking y1 equal to this one. So better to write a different symbol here, and which is corresponding to yi. Okay, so this one is same as 15 plus 1 plus 1 plus 1 equal to 18. And that is the values of y1, this is y2, this is y3, this is y4. Okay. Fine. Now we move to the next phase of this lecture. That is the main important part. So that is the pigeonhole principle. Now the pigeonhole principle, you have already, I think, seen that what is a pigeonhole principle. The statement is very simple, looks like very trivial, but when you apply this in a to solve a problem, it does not look so trivial. But the statement is very trivial. The statement is, suppose that n plus 1 or more, so at least n plus 1 you can say, pigeons are put into n holes. Okay, suppose you have say n plus 1 or more pigeons which are put into n holes, then some hole contains at least 2 pigeons. So it looks very trivial, right? It looks very trivial. So we will also prove this. But do you know how to prove it? So though it is very trivial, but we need to prove, right?
We can prove by contradiction. Let's assume no.
Right. So that is the one good one. So the proof is also trivial, like, so we will use contradiction. So if possible, the statement is not true. What is the statement? If possible, the statement, this one, that some whole contains at least 2 pigeon. This statement is not true. So then, so what does it mean? So that's mean each hole contains at most 1 pigeon. it is fine to write each hole contains at most one pigeon. Okay, so then the total number of pigeon is at most 1 plus 1 plus up to n, since you have n hole, so up to 1. So this is n1, so that is the value is n. And this is a contradiction because we are assuming that we have at least n plus 1 or more hole. So this is a contradiction. Okay, so therefore the statement must be false. So therefore one hole, at least one hole, or you can say some hole, contains at least two pigeons. Okay, so this proves the principle. Okay, now one trivial application of this one, that is very trivial. So suppose, so I can just read that problem because that is very trivial. So suppose you have 13 people, and then you can easily say that at least two share a birth month, right? It is very easy to see because your birth month is only 12. So that's mean your whole is 12. And if you take 13 people, so it is more or equal to n plus 1, right? So therefore, obviously, one month should share two people. So therefore, two people will have the same birth month. So that is a trivial problem. Now another one is, so this problem I will write. Now suppose we have 5 pairs of socks are in a drawer. Okay. Now picking how many socks guarantees that at least one pair is chosen. Now can you give me the answer that, and also give me the solution how you will approach?
Sir, the answer should be 6.
6.
6.
Okay, so how will you prove that?
From
we
the
can,
pigeon or
by
principle.
showing an example, like in worst case, we can choose 5 socks such that, or like all the
No,
socks are
suppose you have to use the pigeon principle, right? So how will you write this problem?
like, yes, first we will prove that for 6 it works, then we will prove that 5 we have a case it will not work. So
No,
this,
but
this will complete the.
then you are proving that pigeon principle, right? I'm saying that okay, you just use that pigeon principle.
Yeah, 5 is number of holes and 6 is number of holes.
Sir, first
Right.
we make a claim that we should take 6 number of socks, and we try to prove that claim through a contradiction.
No, you don't need to prove by contradiction. That's what I'm saying. Because suppose if we ask you that prove it by pigeon principle, then you have to find that what are the number of holes and what are the number of shocks.
Okay, sir.
Sorry, oh, what are the number of what are the first of all holes? So here it is clear that the holes is 5 and pigeon in 6, right? So that is the reason you are saying that picking 6 socks guaranteed that at least one pair is chosen, right? But when you write a problem, then you have to find, right, what are the holes, right? So anyway, this is not a difficult one. I'm just asking that how to prove it. How will you prove? I just want to know how will you approach? Because now during that minor, I have seen that many people actually just mislead from the direction, but I don't know why. For an example, we ask one problem that prove by contradiction. So one have to start. So I told you that when we ask that kind of problem, so main focus is not the how to solve this problem, because that solution can be very easy, but main is that how to prove it or how to give a precise logical argument. But very few people started with let P be the statement like this and let P is not true then this. So most of the people did not try, did not start with that. They they just try to do that this is not a root. That's all. And some of one use that many calculus arguments and root finding roots. So many different things. But they are diverted from the main portion, that they have to first choose let P be a proposition that this. But most of the people, students have not done that. Okay. So anyway, see, finding root, that is said that x is cube plus x plus 1 does not have any rational root. So these are very easy problem. This is not a difficult one. But we don't need that. So we did not ask that. We asked that you know the proof by contradiction or not. So that was our main claim or main aim. So you know or not what is a proof by contradiction. But people, most of the students I have seen that did not give the logical argument. They just tried to show that okay, it does not have any rational root. That's all. So similarly here, so if I ask you that use the pigeon principle, so that's mean what we want. We want, do you know here in this problem which is the pigeon and which is the hole? Do you know this or not? Otherwise, this problem is very trivial. Even you can solve it without using pigeon principle by giving the similar argument. But if I ask you, okay, prove it by pigeon principle, then you have to show only that which are the whole and which are the principal pigeon and which are the whole. Okay, so there are many ways to express this problem. So first of one, so you can just consider 5 pair. Okay, say. So you may give a different kind of solution, different kind of writing, but remember that you have to just find that what are the pigeon and what are the holes. Okay. So here we can write, this is one way. Consider the 5 pairs of socks are colored by 1, 2, 3, 4, and 5 respectively. So each pair we are giving a different number to differentiate them. Okay, so that you can differ them. So consider 5 pair of socks by color this to differ them. Now here, so label the 5 colors with 5 holes. Now these are your holes and label the sock with pigeon. Okay. Now it is very easy to prove by the pigeon principle. Now you can see that if we choose 6 shocks, then by the pigeon principle, right? Or I can write here. Now if we select 6 shocks, then by pigeonhole principle, some color, because so there it had some hole, and here hole is your color, right? So therefore some color must be obtained by at least 2 shocks, right? And so we are done. So since you have at least 2 shocks with same color, so that's mean you have at least 1 pair. So this picking 6 shocks guarantees that at least 1 pair is chosen. Okay, so this is one application of pigeonhole. Okay.
Sir, but in this you assume that converse of pigeonhole principle is true. Like we can say 7 socks also, then we can say 8 socks also, but we assumed only n+1. So like we assumed converse of pigeonhole principle is true.
No.
Because we are given number of pigeons and then we determine holes. But here we are given number of holes and then we determine pigeons.
No, I did not get what you are saying.
Like sir, in this problem, actually we are using converse of pigeonhole principle, because in pigeonhole principle we are given number of pigeons and holes and we determine and we say at least a pair exists. But here they say at least
No. See, here it is given that there are 5 pair of shocks, right? Now
Yes.
these 5 pairs, there you have to first make sure that 5 pairs are different. Now each pair you give a different hole. You just label each pair as a different hole. So that's it. That's it. And then that by the pigeon principle, you can say that if you have at least since you have 5 holes, so 5 plus 1. If you have at least 6 pigeons, then one hole must contains 2 pigeons. So that is the reason you have 6. We are using only pigeon principle only.
But sir, we can in this way say also 7 also and
Right,
8.
7 also, right. It is fine. But
Okay.
what the question says that picking 6 shocks guarantees that at least 1 pair is this. If you take 7, that is fine. But if you 6 shocks is guarantees that, then why you are going to 7?
Yeah, but like, is
But
it
I ask you,
minimum?
no. Here I am giving just the question is that picking 6 shocks guarantees that at least 1 pair is chosen. That is the main question. And
Okay.
I ask you that what should be the minimum number?
Okay.
The question is this one. Okay, the question is this one. I ask you. So picking which is the least number of shocks if you choose. You can choose 10. Then there is no meaning of any solve, right? Because you have total 10 shocks. So you can choose 10. Then definitely you will get not only one pair, you will get all the pairs. So even if we ask you that, right, so in that case, we will ask that what is the minimum number of pairs? If I ask you in that way.
Sir, but if we ask the minimum number of pairs, then we have to show that less than 6 socks will doesn't work. Like this, we also
Right,
have to
right,
show.
right. Yeah. May not work. Right?
Yes, sir.
Yeah, I got what you are saying. But here I'm just telling you that what will be the number which guarantee that this. Right. If we want to say that 6 is the minimum one, then you have to prove that 5 will not work. And that is easy to find. You can just say that, okay, choose 5 one from each pair, right?
Yes, sir. Yes, sir. Like that's what I'm saying. Like, but
Right,
like
right,
we
right.
have to.
Yeah, right. I got your point. Yeah, thank you. Okay, so this is the another application of the Pigeon principle. But when you see this problem, then it does not look like a Pigeon principle. But by using that, you can easily solve this. So I am writing in terms of lemma. So suppose a1, a2, an are integers. Then some consecutive sum, say ak plus 1 up to a k plus n. Okay, so where you can say that k is bigger equal to 1, or which we mean actually, and k plus a k sorry, it is k plus m is less than equal to n. We are meaning that one is divisible by n. Okay, so suppose you have a1, a2 up to an, you have this n integers, and then we are saying that, and we are just rename it a1, a2, so that we can say what do we mean by a conjugative one. So a1, a2, a3, they are conjugative. Okay. Now then, sum of this, we are not saying that conjugative integers. Okay, we are saying that conjugative sum. So that's when we are talking about a1, a2, a3. So we are saying that a2 is conjugative a3 and this way. So in other way, so I have written what is the meaning that conjugative sum. Now if you have some k and k plus m, so that ak plus 1, this conjugative one sum is divisible by n. Okay. Now here, so this is a proof. Now here we use the Pigeon principle to prove this lemma. Now here is the proof. Now first we consider n sum. N sums, say S1 is just A1, S2 is just A1 plus A2, S3 is A1 plus A2 plus A3. In this way, we are writing Sn equal to A1 plus A2 plus A3 plus An. Okay, so we are writing that all the n conjugative sum. Not all possible way, we are writing this conjugative n conjugative sums. Now if one of them is divisible by n, then we are done. then we are done. Right? Suppose S3 is divisible by n. So that's mean we have this conjugative sum and that is divisible by n. Right. Now if not, so if not, that's mean, so if we say that no, none of them is divisible by n. So if not means none of them is divisible by n. So in that case, so let Ri be the remainder when Si is divided by n. And here 1 less than equal to I less than equal to n. Okay, so we have value R1, R2 up to Rn. Okay, so that's mean, in other words, S1 gives remainder R1, this gives remainder R2, this gives remainder R3, and this gives remainder Rn when divisible by n. Okay, so when we divide by n, and now we are saying that each of this Si is not divisible by n. So that's mean each Ri is always bigger equal to 1. Right? So Ri cannot be 0. So since Si is not divisible by n, so therefore Ri is bigger equal to 1. But since we are dividing by n, so therefore Ri is obviously less than n. So thus Ri can take value 1, 2 up to n minus 1. Okay, so that's mean Ri can takes value up to 1 to up to n minus 1. So this is how many numbers are there. So this is n minus 1 total numbers, and you have R1, R2, Rn, and this is total n. So here you have, this is your whole and this is your pigeon. Okay, so therefore one whole must contain at least 2 pigeon. Right? So that's mean one whole must contain, there are some whole which contain at least 2 pigeon, right? So thus one whole, say R, okay, we are not saying R here, we can say it is say K, okay, must contain at least 2 pigeon say Ri and Rj, where I less than j. So that is, in other words, we are saying that Ri equal to K, Rj equal to K. And what is Ri? That is S1 plus S2 plus up to Si. and this is S1 plus S2 up to Sj, and I less than j, and so therefore, oh, not equal to, sorry, how to write this? I should not write in this way. So equal to some say p n plus k, and this is say some q n plus k, where p less than q, right? Because they are divisible by if they divides by n, then the remainder is k. And similarly, if this is if we divide this by n, then the remainder is k.
Sir, shouldn't it be A1, A2, and AI?
Oh, sorry. Right. Thank you. Right. And then if we subtract this by this, since j less than 1, so then therefore this will be this. So therefore a1 plus a2 plus aj minus a1 plus a2 plus ai, that will be q n plus k minus p n plus k, and then that will be ai plus 1 plus ai plus 2 up to aj, that will be q minus p into n. So that is divisible by n. So we are done. Okay, is that fine with everyone? And thank you for the correction. So similarly, we can prove the Chinese remainder theorem as well. So this is one theorem, one lemma, and there is one. So have you heard about the Chinese remainder theorem?
No, sir.
Okay. The Chinese remainder theorem is a beautiful result in, you can say, number theory or algebra. Now it says it has some general version as well. So I am giving here the statement of this. The Chinese remainder theorem. It says, so if m and n are relatively prime. Okay, relatively prime means they does not have any common divisor other than 1. You know, right? What is the concept of relatively prime?
Yes, sir.
That's when GCD is 1. Just. And it is given that 0 less than equal to a, strictly less than m, and 0 less than equal to b, strictly less than n. Okay. Now then this theorem says there is an integer x such that x equal to a mod m, okay, and x equal to b mod n. In other words, if there is an integer x such that if you divide that by m, then a is the remainder and if you divide by n, then b is the remainder. Okay. So again, by the pigeon principle, we can prove it. So first of all, we consider the integer this. So a plus m, a plus 2m up to a plus n minus 1 m. Okay, consider these integers. Okay, so you can see that each has remainder a when divided by m, right? Obviously. Now, if some of them has remainder b when divided by n, then we are done, right? Now, if some of them has remainder b when divided by n, then we are done. Is it fine? Right? In that case, suppose this has remainder b when it is divided by n. It has already remainder a when divided by m. That's mean you can choose your x equal to a plus 2m, right? So this is trivial. Now, if not, so if not, that's mean if not means here. So none of them has remainder b when divided by n. So then what we will do? Now then take R1, R2, Rn. Let this be the remainder when this a plus m, a plus n minus 1 m divided by n. Oh, sorry. So that will be m, right? No. No, I am confusing something, right? You have n ri is the remainder.
Sir, there are n
It
terms.
should be n. There are n terms.
Oh, so this is m. Okay, okay, sorry. Sorry. Right. So they are the remainder when this is divided by n. Right. Now we are fine. Fine. So what we are doing now? Now we are using the same thing. Now here, since each of them does not have remainder b, so therefore here 0 less than equal to ri less than equal to m divided by n, right? Right. So less than equal to n and ri is not equal to b. Okay. So we have r1, r2, rn. This is n terms and ri or 1 less than equal to I less than equal to n. And Ri can take value zero, 1, 2 up to b
Sir,
minus 1. Yes.
here 0 and n should be excluded, right? Because if our remainder is 0, then we are already. Uh, sorry.
Sorry. No. Yeah,
No,
you are fine.
n should only n should
N
be
minus 1.
excluded.
No,
Yep.
no. Right.
No, it's okay.
So, yeah. So this is n and this is b plus 1 up to n minus 1. Right? Now here you have total n minus 1 values, right? Because it is 0 to n minus 1 and b is excluded. So therefore this total n minus 1 value, we are writing this is as my whole. And we have here n values and this is my pigeons. Okay. Okay. So this is my whole and this is my pigeon. And similarly, by the pigeonhole principle, by the pigeonhole principle, we can say that some number, we can write anything, that does not matter. Just leave it. Some number is attained by, we can say must be attended by at least 2 Ri. Okay. So say Ri and Rj where I less than j. So in other words, we are saying that Ri equal to Rj. We are saying that. Okay. Okay. Say some number. Okay, we can say this is R. We are saying that Ri equal to Rj equal to R and I less than j. So what does it mean that it is Ri? So that's mean A plus Im, that is say some Pn plus Ri, which is Pn plus R, and A plus Jm, that is some Qn plus Rj, that is Qn plus R. They are same. So that's mean A plus Jm minus, so here also we have Q minus bigger than P. This is minus A plus Im, that will be cancelled out, Q minus P in. And then we will have,
Sir, it should be a plus I minus 1.
Yes, sir, I minus 1. I mean, it does not make much difference in the proof, but logically, because we are taking I from 1 to n, then it should be I minus 1. Right?
good. Because I am taking that. Okay, we are what we are doing. Two number at least say, okay, I am writing here R plus 1, G plus 1. Then that will be I plus 1, G plus 1. Okay, so we have this. And then that will be into M equal to Q minus P n. But that is a contradiction. Okay, so what does it mean? So that's mean actually, n divides j minus I into m, but m and n is relatively prime, so that implies n divides j minus I. Why? As m and n are relatively prime. Relatively prime. Right? And again, this is a contradiction. As 0 less than I less than j less than n. Or I think 0 less than equal to. No, 0 less than I. Okay, so this is a contradiction. Because since they are two different numbers, so n cannot be divides j minus I. So this is a contradiction. So what does it? So what was the contradiction? So we assume that here if not. Where is if not my if not? If not, then we get a contradiction. So therefore this statement is not true. So therefore we have some number among these n1 which has remainder b when we divide by n, right? So we are done. Is that clear that we are done?
Yes, sir.
Yes. So that's one of them. Them means that is a plus m up to a plus n minus 1 m has remainder b when divided by n. So, take x as that number. So we are done. Okay. Now I am just writing one corollary before closing today's lecture. What you can write it is as a theorem as well, because it is just a generalization of pigeonhole principle. Now it says that suppose that R1, R2, Rn are positive integers. Now if x is bigger equal to x is also an integer. Summation I equal to 1 to n Ri minus n plus 1, that x number of, okay, now this is also integer, number of object are put into n boxes say labeled by 1 to up to n. Then some boxes or some box labeled by I contains at least Ri objects. This is just a generalization of pigeonhole principle. In the pigeonhole principle, we need at least one element. Here you have at least Ri object, and your x is bigger equal to this number. Now again the proof is very simple. Again you can prove by contradiction. So if the statement, what is the statement? This one is not true. We can write star. The statement star is not true. So then the total number of object, total number of object is at most. Okay. So here we are saying that some boxes labeled by I contains at least Ri object. So if this statement is not true, so that's mean all the boxes, okay, contains at most Ri minus 1 objects. So therefore total number of objects is at most R1 minus 1 plus R2 minus 1 up to Rn minus 1, and that will be summation of I equal to 1 to n Ri minus n, right? So this is the maximum number of elements, but here it is given that your total number of object is bigger equal to this. So this is a contradiction. So here we are getting x is less than equal to this number. Right? But it is given that x is bigger equal to this number. So therefore this is the contradiction. Okay, so we are done. So you will find some applications of this Pigeon principle as well. Now you can try the tutorial sheet 6. I have already sent you, and now you can try it. Now all the problems you can try, and in the next tutorial your TA will solve these problems. Okay, and I think you know that you will have quiz on 11th, next 11th, that is 11 October, and that syllabus will be only this combinatorics. That is the 5 lecture of combinatorics. 16, 17, 18, 19, 20. Oh, no, that is from 12, right? 12, 13, 14, 15, 16. Yeah, 12 to 16, not 16, up from 16. So 12 to 16 lectures and tutorial sheet 6 and 7. Okay, then.
Hello, sir.
Yes.
Sir, in the proof of Chinese remainder theorem, what is the contradiction which we have found?
So we get a contradiction where it is. Right. So we have this one, right? So this number equal to this into n. So therefore n divides this number j minus I into m. But m cannot divide m because n and m is relatively prime. So therefore n divides this number. But both of them is less than n. So therefore n cannot divide this number.
Okay, got it.
Okay, thank you. Okay, then we can stop, right?